All right, today we're putting on our detective hats and diving into a statistical mystery. We've got two groups, and yeah, on the surface they look different. But the real question is that difference actually real? Or is it just random chance playing tricks on us? That's the case we're gonna crack.
Okay, so let's get into the specifics. Our case file is all about two brands of cigarettes. We've taken a little sample from each to see how much stimulant they have. And the central question is this: does one brand genuinely have more stimulant than the other, or does it just look that way because of the few samples we happen to pick? So here's our first look at the evidence. We tested 10 cigarettes from brand A, and they averaged 3.1 milligrams of stimulant. For brand B, we tested 8, and that average was 2.7. So right away you see that brand A's average is higher. But take a look at that standard deviation column. That's our first clue that things are a bit spread out within each brand. And that variability is exactly why we can't just stop here. Case closed, right? Not so fast. So why can't we just look at 3.1 and 2.7 and call it a day? I mean, why isn't that simple comparison enough? Well, it's because these numbers come from samples, right? They don't represent every single cigarette made by these brands. And that, my friends, is where things get a little tricky. Here is the absolute heart of the problem. Our sample sizes are tiny, just 10 and 8. That means random chance could totally be fooling us. We might have just happened to pick a few extra strong cigarettes from brand A. Plus, we have no idea what the true variation is across all the cigarettes out there. That measure of variation is called variance, and all we have are these little estimates from our tiny samples. And this brings us to our next big challenge. The sample from brand A had a standard deviation of 0.5, but brand B's was 0.7. These are our clues about the overall variation, but they're different. We can't just pick one over the other. What we need is a smarter way to combine these two pieces of evidence into a single, much more reliable estimate. And that smarter way has a name. It's called pooled variance. Just think of it as our best possible guess for the single underlying variance that we assume is common to both brands. The whole idea is that if the brands are pretty similar, they should have a similar amount of variation. This method helps us find the best single number for it. It's like taking two separate clues and blending them into one much stronger piece of evidence. Now, here's a look at how we actually calculate it. This formula is basically just a weighted average. You'll notice how each sample's variance gets multiplied by its sample size minus 1. What this does is it gives a little more weight to the evidence from the larger sample, which in our case is brand A. It's a really logical and smart way to combine our information. So now that we've got our special tool, the pooled variance, we can finally get to the main event, and that is building a 95% confidence interval. This is going to give us a whole range of plausible values for the true difference in stimulant content between all of brand A cigarettes and all of brand B's. Let's walk through how this is done. First, we take the square root of that pooled variance to get what's called the pooled standard deviation. That comes out to 0.596. Next up, because our samples are small and we're using an estimated standard deviation, we can't just use the good old normal distribution. We have to use its cousin, the t-distribution. So for all you students out there with a t-table, the first thing you need is the degrees of freedom. The formula for that is simple. Just add your sample sizes and subtract 2. So 10 plus 8 minus 2 gives us 16. You look down the DF column to 16, then go across to the column for 95% confidence, and boom, the table gives you the number 2.12. With all those pieces, we can calculate our margin of error and build our interval.
And here it is, the big reveal. After all that work, our 95% confidence interval for the real difference between brand A and brand B is a range from -0.2 to +1.0. This single range is the crucial piece of evidence our entire investigation has been building towards.
So we have our range. We did the math. But what does it actually mean? This right here is the most important part of any statistical case, the interpretation. What is this interval really telling us about our two cigarette brands? The rule for cracking this particular code is unbelievably simple. When you're looking at a confidence interval for a difference between two things, the one magic number you are looking for is 0. The whole question is, does our interval contain the number 0? Now, this is where it really clicks. Look at the comparison here. On the left, in our cigarette case, see how that interval from -0.2 to +1.0 goes right over 0? That means a true difference of 0 is a totally plausible value. We simply cannot rule out the possibility that there's actually no difference at all. Now compare that to a hypothetical light bulb case on the right.
That interval is entirely positive. It starts at 6. Since that range does not contain 0, we could say with confidence that, yes, a real difference exists.
Okay, so we've reached our verdict. We haven't found a significant difference. But a good detective always double checks their work. Our entire method was built on one very important assumption we made right at the beginning. The question is, was that assumption a valid one? Remember way back when we decided to pool the variances together into one number? Well, that step was only okay if we could assume that the true underlying variances of both brands were roughly equal. We kind of need to do our due diligence here and actually test that assumption. And to do that, we bring in another statistical tool, the F-test. Now, the F-test is clever. It doesn't look at the difference between the variances, it looks at their ratio. So we're going to build a confidence interval for the ratio of the two population variances.
The logic here is just beautiful and simple. If two numbers are equal, right, say sigma 1 squared is the same as sigma 2 squared, what happens when you divide one by the other? You get 1. Every time. So our test is pretty straightforward. Let's create a confidence interval for this ratio and just see if the number 1 is inside it. So we use something called the F-distribution, which is another one of those statistical tables. A lot like the T-distribution, but it's designed specifically for comparing these ratios of variances. And after we run the numbers, we get a 98% confidence interval. The result is a range from 0.076 all the way up to 2.862. And this is our final check. Does our interval contain the number 1? Yep, it absolutely does. It falls right in there. This tells us our initial assumption to use the pooled variance method was totally sound, which means our original verdict stands. Based on the evidence we have, there is no statistically significant difference in stimulant content between brand A and brand B. Case closed. For real this time. And that really gets to the core of what we've done. I mean, we saw a difference in our samples, right? 3.1 versus 2.7. But using statistical inference let us figure out that this difference just wasn't big enough to be considered real. It could easily have just been the random noise of sampling. For a consumer, it means you can't be sure brand A is stronger. For a regulator, it means there's no evidence to back that up. So, this whole case was built on that assumption of equal variances, and thankfully we tested it. But it leaves us with one final really important question for any data investigation you might do in the future. What other hidden assumptions are you making without even realizing it? And how can you be absolutely sure your conclusions are built on solid ground?